In today's video, we are going to discuss the software required for an in-situ assessment of leaf area index using IoT-based agricultural system. Now, along with hardware components, software plays a very important role in collecting, processing, analyzing, and visualizing agricultural data in real time. So, let's explore the major software tools used in this smart agriculture system. Now here you can see the software architecture and workflow of an IoT-based agricultural system for in-situ assessment of LAI. It explains how the software components manage the data collection, processing, communication, and monitoring in the agricultural field. Now at the core of the system is the TinyOS, which is an open source and low power operating system designed specifically for wireless sensor networks. And this TinyOS, it controls the operation of Telos B sensor modes and manages communication between the devices. It is widely used because of its energy efficient design and support for low power sensing applications. Now the system collects the environmental data using the Telos B modes, and these Telos B modes are deployed in the crop field, and each data packet generated by this, it will be having a timestamp and the sequence number that is represented by SN here. The timestamp, it records when the measurement was taken, while the sequence number helps identify and track individual data packets during the transmission. So here you can see two deployments, two deployment generations with different sampling rates. First is the wired deployment, it is the first generation. Second is the wireless deployment, it is the second generation. Now in the first generation wired deployment, sensor collects data at the rate of 30 samples per hour because power and the communication resources are readily available. Now in the second generation wireless deployment, it uses only 6 samples per hour to reduce the energy consumption and extend the battery life. Now here one of the key feature of the TinyOS is its low power listening mode. When a sensor mode is not actively sensing or transmitting data, the TinyOS automatically switches it into a sleep state, and this significantly reduces the power consumption and it will increase the operational lifetime of the sensor modes. Now here the ground sensor nodes, these will continuously monitor the environmental conditions and broadcast the data frames, and these transmissions are received by the Raspberry Pi, which acts as a cluster head here. And the Raspberry Pi, it performs multiple functions including collecting the data from the sensor modes, storing information temporarily, and managing communication and monitoring the health of the sensor nodes. Now, one of the important capability of the Raspberry Pi is its ability to automatically reboot faulty sensor nodes. Now, if a Telos B mode stops functioning correctly, the cluster head detects the issue and restarts the node without requiring manual intervention, and thus it improves the system reliability. After collecting the data, the Raspberry Pi, it forwards it to a gateway, which then transmits it to the IoT cloud infrastructure. Now the cloud platform, it stores, processes, analyzes and visualizes the data, and the farmers and the researchers can then access real-time information for crop monitoring, LAI estimation and decision making. So the overall here the software architecture, it ensures efficient, reliable and energy conscious operation of the smart agricultural monitoring system. Here in this image you can see the IoT architecture of this LAI assessment system, which is used for smart agriculture. And this architecture, it enables the data collection, communication, processing, visualization and user notification through an internet-based platform. Now here you can see the wireless sensor network, that is a WSN, which consists of several Telos B sensor modes deployed in the crop field, and these sensors measure the environmental parameters such as the temperature, then humidity and the light for that is a PAR for the LAI. And a Raspberry Pi, here it acts as a cluster head and collects the data from all the sensor nodes and forward it to a gateway. Now the gateway, it sends the collected information through the internet to a central server here, And at the server side, an MQTT broker receives the data from the WSN. And MQTT, it is a lightweight publish or subscribe communication protocol, which is commonly used in IoT applications because of its because of its efficiency and low bandwidth requirements. The server, it also hosts an Apache server, that is the web server, which is a GUI here, which provides graphical user interface for monitoring the system. Now the sensor data is processed and visualized directly on the server through the charts, graphs, and the dashboards. Now one of the important feature of the system is the alert notification mechanism. Now if a sensor node fails or an abnormal condition occurs, the server automatically informs the registered user, and the user receives notification on a smartphone application. So the smartphone, this here, it will display the real-time sensor readings. Then it displays the LAI values, system status, battery information, then historical trends and the alerts. Thus, the IoT architecture enables continuous monitoring, quick fault detection, remote access, and efficient decision making for the precision agriculture. Thank you.